Welcome to qnawire.
Alright, so we have a lot going on in this problem, namely a chair with various forces acting on it. So for simplifications, we're going to draw our chair like that, like a nice little square, and then take a look at the forces that are being acted on it in order from easiest to least obvious. So I think the most obvious force that is always going to be acting on the chair is the force of gravity. So that's going to be equal to the chair's mass times the acceleration due to gravity. And in order for the chair to not go anywhere up or down, we're just sliding horizontally in this problem, there has to be some sort of vertical force to counteract the force of gravity. And this is the normal force of the floor pushing back up on the chair. We do also know that you are applying a diagonally downward force. We're just going to call that F. And we know precisely which angle you are applying that force at. And that is going to be at theta, or in this problem, 37 degrees below the horizontal. So theta is going to be equal to 37 degrees. And then lastly, we are told that this is not a frictionless surface. So because the block is sliding to the right in the way that I've drawn it in this problem, we will have a kinetic friction acting to oppose this motion. So that is going to be directed to the left. So that completes our free body diagram, and that was part A of the problem, by the way. So in part B, we are tasked with calculating the normal force. So there are a lot of forces on this block and lots of distractions. We tend to associate any frictional force with the normal force via a coefficient of friction, whether that be static friction or kinetic friction. But one big indication that that's a red herring in this problem and that we won't need to use all the information given in this problem is that they don't even tell us what any coefficient of friction is. So again, it's one big indicator that we don't need to use all the information that's given to us in this problem. So the fact that we're solving for the normal force hopefully tells us that we should be applying Newton's second law in the vertical direction. So I'm going to call that the y direction. And we actually don't even care in this problem about any of the forces in the x direction because this is all the information we need. And we don't have to use all the information in the problem. So to just tally up the forces, calling up positive and down negative, being really careful with our trigonometry, we see that we only need the sine component of our applied force because it's the only diagonally oriented force in this problem, so we only need one component of it. But that's how you would apply Newton's second law to the setup. So now we're just going to rearrange it in order to solve for the normal force. So I'll go ahead and do that. Just add the other two terms to the other side of this equation, and then we are actually free to plug in numbers now. All right, so run that through a calculator, and then you will get a normal force of 142 newtons. Okay, and that's all you had to do for this problem.